Geometric actuation is the property where a physical shape's movement intrinsically produces a calculated result. A physical tool, like a slide rule, does not run an algorithm. The geometry itself is the math, providing absolute structural certainty. In 1945, computing architecture abandoned this approach. We sacrificed analog geometric hardware in favor of systems that simulate computation using disconnected symbols. This decoupling gave us symbolic computation. It enabled infinite scaling and substrate independence, allowing a single program to run across countless machines. But in making that trade, we lost autocoincidence. That is the physical property where a system's current state and its historical record are the exact same physical object. Modern heap memory relies entirely on symbolic pointers. These pointers completely decouple semantic meaning from actual physical hardware coordinates. Because meaning and memory are physically separated, we can no longer physically verify if a system is performing its authorized role without relying on the software to verify itself. This separation produces alignment decay. It is the direct, silent consequence of utilizing decoupled symbolic pointers to maintain complex logic. Current large language models encode semantic meaning into high-dimensional floating-point vectors. These vectors have zero fixed relationship to physical CPU addresses. The industry attempts to solve this architectural drift using more software. They layer Turing-complete algorithms like reinforcement learning from human feedback or constitutional AI over the base models to monitor behavior. Rice's theorem exposes the mathematical limit of this approach. A Turing-complete system cannot verify its non-trivial properties without initiating an infinite regress. This creates an asymptotic verification ceiling. The computational overhead to verify the system grows geometrically, yet the structural certainty never reaches 100%. AI alignment cannot be solved with better algorithms or additional oversight software. It is a physics problem, requiring a return to the hardware substrate. The solution is the Semantic Physical Hierarchical Memory Grid, or SPH. We engineer a memory substrate where a data element's semantic rank perfectly matches its physical location, and the primary engineering mandate required to achieve this is the total mathematical elimination of the symbolic pointer. We replace the pointer with the short-rank compositional address function. This equation calculates exact physical byte offset addresses strictly from a node's semantic rank. It utilizes direct integer arithmetic, eliminating floating-point calculations. The function is scale invariant. It packs hierarchical children into the exact contiguous coordinates of their parent, bypassing lookup tables completely. By mathematically fusing semantic rank to byte offset addresses, the hardware inherently knows where data belongs. True geometric actuation is restored directly to the silicon layer. This layout is enforced by physical CPU hardware, identifying the L1 cache controller as the rigid sub-turn gate that governs the S equals P equals H structure. The architecture relies on a strict stride integer inequality. This rule guarantees that parent address spans physically encapsulate their children without aliasing. This creates the Gestalt gap. It is the specific cache line boundary separating distinct, unrelated semantic blocks in physical memory. When external reality shifts, a data element's semantic weight changes relative to its neighbors, forcing the system to reorganize. This rank change mathematically forces the data element across the Gestalt gap boundary, resulting in an immediate physical eviction. Semantic drift is translated from an invisible, abstract software failure into a highly measurable physical hardware event, a cache miss. The system monitors this using the CPU's Hardware Performance Monitoring Unit, or PMU, as a native zero-overhead drift sensor. The PMU inherently monitors cache line boundary evictions. It operates at the silicon level, reading data entirely below all software abstraction layers. Once the accumulated drift metric crosses a set threshold, the PMU fires a direct hardware interrupt. This triggers the tesseract maneuver. The hardware responds instantly, utilizing an atomic compare and swap instruction to secure the pathway. This atomic pointer substitution executes in roughly 5 nanoseconds. Classical software-measured control loops require 300 milliseconds. Every cache eviction dissipates physical heat, defined strictly as Landauer's principle of joules per bit. The control loop detects and acts upon this fundamental physical inefficiency. The zero-drift control loop physically forces semantic integrity in nanoseconds, completely replacing the guesswork of probabilistic software with the absolute determinism of hardware physics. Ungrounded generative systems rely on probabilistic retrieval, where certainty is always less than 1. Physical positional equivalence operates with absolute 100% certainty. This chart graphs the signal survival equation, defining the temporal decay factor where every ungrounded boundary crossing irreversibly destroys 0.003 bits of positional information. At the 160 hop event horizon, the system drops into chaotic noise, shaped as grammar. The S equals P equals H memory grid entirely sidesteps this decay. By spatially pre-aligning the data, it eliminates read-time boundary crossings. This architecture does not verify objective universal truth. It guarantees structural honesty, proving at the silicon level that the machine's internal state identically matches its programmed intent. This measurement allows us to quantify trust debt, that is, the direct, dollar-denominated financial liability derived from signal survival degradation in mission-critical AI. The hardware cache miss rate natively outputs the unforgeable RC metric. This allows us to quantify operational risk without relying on self-reported software logs. Under strict regulatory frameworks like the EU AI Act, oversight requires continuous, tamper-proof proof of an AI system's role alignment. Hardware telemetry enables an actuarial insurance market. AI liability can be priced based on physical drift measurements rather than theoretical arguments. The ultimate advantage of geometric actuation over symbolic approximation is absolute determinism. True AI verification is impossible inside software layers. It is only achieved when we abandon simulated certainty and hardwire semantic meaning back into the unarguable physics of the substrate.